So once again, we're on page 415. We're talking about the pinhole camera, and what we need to talk about first is this term, linear propagation. So that's what we're looking at right now. Light travels in straight lines, and that is in the same medium. So I talked about the fact that if light travels into glass or if it travels through water, it is going to change directions, but it's not like in a curve. It's in straight lines. So light travels in straight lines, and the term that is given for that is linear, meaning line. Propagation means as it goes forward. Okay, so it goes forward in straight lines. A beam of light is a stream of light rays. Someone asked me the other day about the difference between a beam and a ray. They're very similar. In our common language, we're going to talk about a beam of light being a collection of smaller light rays. If you think about a line is like an infinitely small collection of points that make a line. So we're really talking about beams of light or light rays. We're going to draw diagrams called ray diagrams, and so we're going to draw one single line, and that's going to represent a ray. So when we talk about a beam of light, we're talking about, many rays of light shining and traveling. The stream of rays can be converging, they can be parallel, or diverging. So in a beam of light, this stream can be converging, which means coming together. So converging means they can be traveling towards each other, like this. They can be parallel. You guys know what parallel is. Traveling always the same distance apart from each other, never intersecting. Or diverging. Of course, diverging would mean that they would be traveling, again, straight lines, but away from each other. So that's the difference there. Converging, parallel, and diverging. So the transmission of light allows for a very simple kind of camera to be constructed, called the pinhole camera. So because light travels in straight lines, we're going to see in this video that we're going to watch in class here how a pinhole camera can be made. And literally a pinhole camera has an opening that's just made by a little pin, so that very few rays of light are able to enter, and you'll see how it works in a second. But this transmission of light allows for a simple camera called a pinhole camera to be constructed. And I do have one that I made with a student last year, and it doesn't work real well because it's tough to get the camera to work properly, that you see a clear image. But like I say, in the video you'll see how they can work. Most of us, when we think of a camera, we think of a lens that focuses light onto a film or a digital detector. So I don't know how many of you take pictures with single lens reflex cameras or DSLRs. Anybody have one or use one? If you've ever taken a picture with one and it doesn't have manual focus, what you realize is that you have to shift or you have to turn the lens in order to get a sharp image, right? And that's basically bringing the lens further or closer to the actual, the viewer. In a pinhole camera, right, and if we go back to this right here, in the pinhole camera, you can slide this inner cylinder in closer or further away to sharpen up the image. But there is no lens that's refracting the light. Okay. Now, a lens bends light, which we're going to talk about lenses a lot coming up. But this is a camera without a lens. A lens actually takes a ray of light, and instead of having it go straight through like this, it actually alters its path so that it comes in at a different angle. And the same thing over here, comes in at a different angle. So this is a real basic kind of camera with no lens. That's why the image is upside down always. So let's see if I can do this. Right. A camera can be anything that allows the formation of an image on a film. It doesn't have to have a lens. So let's take a look at some diagrams here, and you might want to draw these down as we talk about them. And this may seem odd at first without a lens. How is an image supposed to be made? The trick in forming an image is to make sure that that the light only shows one point of view. So that's why the hole in the camera must be pretty small to let very few rays of light through at a time. If the hole is big, what happens is there's lots of light rays and they basically start to overlap each other and you don't see a clear image. So if you have a small hole in this pinhole camera, then you have very few rays of light coming through and you're able to sharpen up that image. Now I've shown you this one that we made last year, and like I say, we had to alter it quite a bit in order to get a good view. And mostly what you get here is a puff of light on your eye. But I actually can see it's tough to get a sharp image, but you can actually sort of see as you move around. You can kind of see light coming through and things kind of move in opposite directions. So what I'll get you to do is I'll just pass this around, and if you could just kind of take a quick look through this side that has some sort of red plastic on the back here. That's the side you look through. And if you just look towards the window, you'd be able to see, and you move it up and down, you'll be able to see that things are changing. You won't be able to see a clear image with this one, but just kind of look through and you can see that there's different rays of light. And actually that one that we made is probably more like this because everything is a bit fuzzy. Okay, so the hole is probably a little bit too big, so that's why we don't get a sharp image. All right. A pinhole camera, okay, allows an image because of the very tiny opening, which we saw in the video. Since light travels in straight lines, tiny opening, since light travels in straight lines, making it so there's only one path the light can take, one image can form. All right. So if you have a very tiny opening, you see an image that will form on this screen of the camera because light travels in straight lines. If the opening is too large, such as the one that the student and I made, probably just a little bit too big, it's tough to get a sharp image. And there's many viewpoints coming, so there's lots of light rays from different objects that are overlapping, and the image doesn't quite form. But like I say, in this pinhole camera, if that's the right size, then you get very few light rays coming in. Okay? What I do want you to notice too is that there's two triangles here. There would be a triangle here on this side of the camera, and there's also a triangle on this side of the camera. And those triangles will always be the same shape but different size. And we're going to make good use of that in future classes here. Okay, so if the opening is too large, a proper image does not form because there are too many viewpoints. In a pinhole camera, we can also control the size of the image by controlling how far away the back of the camera is and how far away the object is from the pinhole. So if you look out the window with that pinhole camera and move it up and down, you can kind of see fuzzy images, and the buildings that are far away, will be bigger than the images that are closer, obviously. And so this diagram kind of shows that if the camera depth, if it's small, you get a small image. The larger it is, you get a larger image. If the object is moved closer, the image grows. The screen is moved closer, the object shrinks. The object size and image size are related by a mathematical formula called the Magnification Formula. And on page 17, we're going to study this Magnification Formula right here. All right, so on page 417, you see the Magnification Formula, which is, it's easy to remember, hi, ho equals di, do. It's like a little rhyme that you can use. Hi is the height of the image. That's what Hi stands for. And Ho is the height of the object that we're taking the picture of. Okay? So Hi over Ho, that is a ratio of those two distances, should always be equal to di, that is the distance of the image from the hole, from the pinhole, divided by the distance of the object from the hole. So if we look at this diagram to see where those distances are, here's the camera, and HO is the height of the object, HI is the height of the image. The distance of the object is literally the distance from the object to the pinhole, the edge of the camera, and the distance of the image is from the front of the camera to the back of the camera. And I mentioned earlier that we are going to use similar triangles, and so if you take the height of this triangle and the height of this triangle, oops, then what happens is you can write that simple proportion, and that's what we're going to make use of here, okay? So this ratio of the base of the triangle over the height of the triangle is the same as the base of this triangle over the height of this triangle because they are similar. So the same shape but different size. Okay, so this is important. Now if you know the height of the image, and if you know the distance of the image because you know how big your camera is, and you know how far the object is, you could calculate its height. Or let's say you know the height of the object and you're going to try and find out, where how far the camera needs to be away to form a good image. You can calculate the distance here that you need to be away. So if you have 3 of these quantities, you can always solve for a 4th one. Okay? Alright, so we'll pause here and take a look at the textbook here, page 417, and we'll maybe do a sample problem together. We should also talk about this, that the magnification of the camera would be either of these ratios, HI divided by HO. So that is the height of the image divided by the height of the object. So if you have a large tree and you have a small, image of a tree, the magnification would be a small magnification, would be a lot less than 1 because you're shrinking the image is smaller. And so if you have a magnification that is 0.5, let's say, then the image would be half the size of the object, 1 over 2. Right? And so this also equals M also equals DI over DO. Image is always on top, just remember that. Image always on top. It gives us the fact that the height of the object is 8 meters high, 8.0 meters high. You want to write this down. The distance of the image from the front of the camera to the back of the camera is 20 centimeters, and the distance of the object away from the camera is 80 meters. So this would be a tree or something of some sort. It says, what is its magnification? So it's asking for M. Okay? That's one of the things that it's asking for. So, can we figure out what the magnification is here right away? We have distance of image and distance of object. If we go back to what we wrote here, we could find the magnification here right away. So, can I just do this then? Magnification equals 20 over 80? No. Okay, you're right. You can't do that. Why? Because these are different units, and that definitely has to change, right? So how can I write this? Let's write the meters in centimeters. And how many centimeters is 80 meters? 8,000 centimeters. You times this by 100. So the magnification here now, when we do this division, what do you get there? Go ahead and do that on your calculator. 20 divided by 8,000 is 0.0025. Right? So that's tenths, hundredths, thousandths, 10,000ths. 25 10,000ths of its original size. 0.0025 is the magnification. And can we calculate also the height of the tree? The height of the image? Right? Because we have the height of the object. What's the height of the image on the camera? How big will it be on the camera? Well, we could use this magnification, or we could go back to our, your original proportion here. Hi-ho equals di-do. Very important. So we got high, ho equals di, do. That's always good to remember. And we can substitute HO, we can substitute DI, and we can substitute DO, and we can solve for HI. So let's do that. They do have to be in the same units, yeah. We're going to make sure they're in the same units. And then we can convert back at the end if we want. So HI is here. What's the height of the object? 8 meters. So let's do that, everything in centimeters. So what's 8 meters in centimeters? 800. Very good. The distance of the image we said was 20 centimeters. And the distance of the object was 8,000 centimeters. So if you get to this point, you want to solve for HI, we multiply both sides by 800. Okay, so 800 comes up here. And this is what you have. You have HI equals 20 times 800 divided by 8,000. Okay. If you want to do this, 2 zeros there and 2 zeros there, it's like dividing both by 100. You can do that, but if you're using a calculator, it probably doesn't really matter. So this is 160 over 80, which is what? 2, and what's the units going to be? Centimeters. Okay. See, if you do it that way, simplify, you don't need your calculator at all. So the height of the image on the camera is 2 centimeters. Yep, so just a reminder that the magnification does not have any units because it's just how many times bigger or how many times smaller. So a factor of 0.0025 smaller, that's what the image is. And the other question was scientific notation. Yep, you can write this as 2.5 times 10 to the negative 3. No problem. And any of your answers you can write in scientific notation if it makes it easier. That's what scientific notation is there for. Alright? So to conclude these notes for just for this little lesson on the pinhole camera, I do want you to read page 410 to 417. That kind of gives you the full story of the notes that I've given you. But I also want you to notice from the video and from our talking that the image is always upside down in the camera, and the term we use for upside down is inverted. Okay? Inverted. If an image is upside down, it's inverted. Now, here's something else, too, that we'll talk more about as we move through, but an image that can be formed on a screen is called a real image. Okay, so it can be formed on a screen, and in this pinhole camera, of course, the image that we're looking at is on the screen. So that is called a real image. The other type of image is a virtual image. And a virtual image cannot be placed onto a screen. Cannot be put onto a screen. So this would be like if you're looking at your image in a mirror. Okay, that is a virtual image because the image that you're seeing is yourself and it would appear to be behind the mirror or behind the wall, right? That's a virtual image. This image that we're projecting onto a screen, and we're actually looking at the screen and seeing the image that's on the screen, that's the definition of a real image. Okay? So real image versus virtual image. That's something that's going to come up a lot. Okay, and right now I'd like you to do the questions on page 418, number 1 to 3. And you have the rest of this class to do these questions and to finish up any other questions that you maybe haven't done or to catch up. So 1 to 3, show all your work.